Now I can come back to the smooth morphism. So, see, the point is, suppose you have a map, say A from X to Y. Assume that F is dominant. So, dominant means that you take the image and closure is Y. Y is Fx bar. That is Y equal to Fx bar. Because that is what you are interested. Other than, it's no point. I mean, without loss of generality, we can assume F is dominant. You would like to know how this F. So, if we take a point in Y, then I can talk about base change at Y, right? I can think as this is a subvariety here, and you have a map from X to Y, then you consider this XY, the fiber product. That is the fiber, and this is, so these are all varieties of under base change, these are all varieties. So, this is a variety over this point. So, this is called fiber. So, now you want to know the what is this fibers, how these fibers looks like. So, these are subvarieties of X. So, how they behave? Are they irreducible? Answer is no. So, how do they behave? How the fibers look like? So, are they irreducible? First question is, are they irreducible? Answer is no. Most of the time, no. Are they smooth? Suppose X and Y are smooth. Both X and Y are smooth. The fiber XY is smooth. Answer is no, not always. You need some extra condition, which is called that if the morphism is smooth. If the morphism, I will give a definition of what is called morphism as smooth. If the morphism is smooth, then only it is the case that fibers are smooth. So, that means if you take Y to be point, so then the morphism is smooth means X to point is same as saying the X is smooth. The fiber is X itself. So, that is how always you should think like this, that whenever you have a map from X to Y, you have some definition for your variety and you want to make it for your morphism. That means fiber should have that property, right? So, that is how always think. So, but there are some generalities that this is not, so on one, okay, another thing is what can you say dimension of xy? Is it dimension of x minus dimension of y? So, it is image, I am taking always dominant. So, that means dimension of x will be always greater than equal to dimension y, right? That will be always the case, because after all, right. So, now is dimension xy equal to dimension x minus dimension y? Answer is no, but this is true. Answer in general no. But there is a, in fact, there is a inequality. It is always greater than equal to dimension x minus dimension. And it is an equality in the most cases. That means, like, most cases mean there is an open subset of y. In most cases, it is cases, that is, there exists an open subset. So, x, y irreducible. I assume x, y are affine. I assume x, y affine varieties, no problem. X, y irreducible. You can do it for any variety, but for simplicity, assume x, y affine variety, because this dimension count, these are very local case. So there is an open subset such that this dimension of xy is equal to dimension of x minus dimension of y for all y belongs to U. That means so if you consider the f inverse of U to U, this map, the dimension behaves well. It just gets added. Okay. So this is the case. So I leave it as exercise. Assume xy irreducible quasi affine or affine exercise. Okay. That this dimension of xy is always greater than or equal to dimension x minus dimension y. So this is an application of Noether normalization. See, finite. You remember that what is Noether normalization? This is application of Noether normalization. Hint. And so, but what I was saying about the theorem of Chevalier, this fiber dimension is a locally what is it called? Upper semi-continuous function. Huh? I will come to that. Yeah, upper semi-continuous. So this is theorem of Chevalier. Which says that suppose f is a map from x to y dominant, and you consider x of k is all those x in x such that dimension of f inverse of f of x is greater than or equal to k. Consider all the points in x such that dimension of f inverse fx is greater than or equal to k. This is, of course, it's in x. This is closed. So whenever you have some function, so upper semi-continuous means if you suppose x to say some z, if you have a function x is a, and if you consider this all those x such that f of x greater than or equal to k, if this set is closed, you could call it's upper f is upper semi-continuous function. K is integer here. So if you don't like k, then I will put some other, say xl. L is some integer. So what does it say? So now this theorem says that the dimension when you take, suppose you have some map x to y, and you take some open set here. Now you have this for every x here, you have, or every y here, you have some xy. Now you are considering xy. Now if you take the closure in y, so suppose u is y minus point, right? So suppose at the point of u, you know the fiber dimension, and you don't want to know at the special point, the specialized y at the point, the closure, you want to know the dimension fiber. So what it says that dimension will only go up at that point. Suppose you have a function x to y, and over u, you know how the function behaves, or you have some information, but at the point you don't know what is that. But this theorem of Chevalier is important. It says that at that point of specialization, this is called specialization. At the point of specialization, the fiber dimension will only be, it will be greater than what it is in the. So this is how, this is a application. I mean, you have some information, right? Once you have some information about dimension, you can guess what it is. If the dimension goes down, so it cannot go down, it can only go up. Like in the blow up case. See, in the blow up case, other than this point, the fiber is just one dimension, just one point, right? But if you take that, if you add at the special point where you are doing the blow up, it will be a Pn minus 1. So fiber dimension is jumping. Right? So proof is, I'll just give a very brief sketch of proof. So if L is less than dimension of x minus dimension of y, then it follows from this exercise. Where is the exercise? This exercise, that there is an open subset where the dimension it is equal. So in the complement it is more, right? More than dimension x minus dimension of y. But the L which you have chosen is less than dimension of x minus dimension of y. So obviously then in the complement of U, the dimension of x y will be greater than equal to L. So if L is less than dimension, then follows from the exercise. And if L is greater than equal to, L is less than equal to, if L is greater than dimension of x minus dimension of y, then what you do, you reduce it to the case, so you apply induction. So induction on dimension of y. So when dimension of y is 0, it is obvious. So now you use this case. So what you do, induction on dimension of y. So let V be the open subset such that dimension of x y is equal to dimension of x minus dimension of y for all y belongs to V. Now you consider y prime, which is y minus V. Now y prime is a proper closed subset, right? So dimension of y prime is less than dimension of y. Now your set, which you call it XL, this XL will be inside pi inverse of y prime, and this is y prime, right? Now pi inverse of y prime is a closed subset in here, so this is a closed subset because pi is a morphism, x, it is a morphism. So only thing to say that this is a closed subset here. But that follows from the induction hypothesis that if it is a y dimension of y is less than, if it is less, then it follows, then it is true. So here y prime, the dimension of y prime is less than dimension of y. So this follows. So apply induction. So this is a very rough sketch. I am not completing the proof, but you can go and complete the proof. Apply induction hypothesis. on dimension y. So, this is a very important theorem of Chevalier, that see dimension, when you have a family x to y, if you have a family of varieties, see the way you think morphism is a family of subvarieties parameterized by y. Whenever you have a family of varieties, then the dimension at the limiting point, the dimension always goes up. So, this is he observed, this is his theorem. Okay. So, as a, some useful corollaries, so I will not prove, I will not give a detailed proof, but I will just state. So, first corollary is that, so the points where the fibers are isolated, mostly that is the case. See, if you have a morphism, say x to y, see you take a point y here and consider the inverse image, this f inverse y. The 5, so most on the open set U, right. So, mostly the points are isolated, right. So, the point in X such that f inverse of f of x are isolated. Are open. So, mostly whenever you have morphism x to y, most points are, they are scattered, they are inverse image. That is what you expect, right? I mean, whenever you have a morphism, it is not that there is a dense open subset where everything is collapsing to a point. It may happen in some strip, right? It cannot happen on a dense open subset. So, this is one observation. The second after observation, if f is proper, then yk, the set of all points y in y, such that dimension, or say yl, dimension of f inverse of y is greater than equal to L, is closed. That is because upstairs it is closed, and if it is proper, the proper takes closed subsets to closed subsets. So, it is closed. And this is most important application of Chevalier's theorem, and I will not give a proof, I will leave it as exercise. So, first two are kind of obvious. So this is as an exercise. Suppose f x to y is proper. And all fibers are, see, first of all, fibers are not always irreducible, right? If you have a morphism from x to y, then the fibers are not always irreducible. So, and all fibers are irreducible. And have same dimension, then x is reducible. So, sometimes you don't know about x, but you know the fibers. You have some information about fibers, but you want to prove something is irreducible. So, it says that x is irreducible. But this is a direct application of Chevalier's theorem. Dimension of the
fibers can be related to other properties only like based on just a particular fiber dimension can be
the fiber dimension will be always greater than or equal to dimension of x minus dimension of y. That is always true. Yeah. But the one thing I will come into, when the map is smooth, then this is the case always. And it is related to the tangent space dimension. I will just come to that. That is the next definition. See, if it has, if you have at one point, if you have multiple fiber, if it is, suppose if the fiber intersects, that point won't be smooth, right? If you have, that means it will have two component. Whenever you have a variety, and if it has two components, at the point of intersection, it's not a smooth map. So multiple component has something to do with smoothness. So that is why that is the next topic, that so smooth morphism between algebraic varieties. Definition: f x to y morphism. So, assumption is that x y smooth, and then f is smooth at x, f. So, whenever you have a map of varieties, you have map of tangent space. So, d of f x at tangent space of x at x to t y of y, where y equal to f x. We have the tangent space level map. If this is a linear map, right? K-linear map. If this is surjective, if is surjective. See, in the case of, say, function of real variable, say one variable, if you have a function from R to R, suppose the function, the derivative does not vanish, then locally it has the inverse, right? You have this 1 by x kind of. You can, or if the f dash x does not vanish, then you can have a local inverse. But in algebraic geometry, even in differential geometry, so this is the case, that whenever you have a function is the Jacobian does not vanish, then you say inverse function theorem. It's called something called inverse function theorem, right? Such thing is missing in algebraic geometry. For example, you take just function x to x square. Suppose a1 to a1, x is going to x square. So at the point say 1, it is 2. It is invertible. It's non-zero, right? But you don't have inverse at 1, because root x, to make it, root x is not a polynomial. You have to go, it has to go to root x, right? Or y has to go to root y. But root y is not a polynomial. So inverse function theorem does not hold in the case of this is a limitation. But you can do something. So that's why what you do. So Zariski topology is very big topology. So you can do some local homeomorphism, like covering space. So locally isomorphism. So that kind of definition you can put, and they are called étale morphism. When the tangent spaces, they are isomorphic. In this case, tangent spaces are isomorphic. So these are called étale morphism. You don't have inverse, but it is not very far from isomorphism, local homeomorphism. You don't have inverse, but tangent space level they are isomorphic. So locally, you don't lose much information, but you really cannot construct the inverse. So these are called étale maps or local covering space. Yes, it's like a covering space. Yeah. So this is the motivation So let me so for example, this example x going to x square, at 0 it is not smooth, it's not smooth, but other than 0 it is smooth, right? Because this is a, at the tangent space level it's a non-constant map, it's one dimensional, so it will take vector space this to this is isomorphism, so it is surjective. So if we smooth, or if we smooth at x not equal to 0, so this is a smooth map. So a1 minus 0 to a1 minus 0, if you consider this map, x going to x power n is a map, example of a smooth map. But at the point 0 is a problem. Okay, so now, so this is the proposition which is the most important proposition. If map from x to y, a morphism smooth morphism, then and xy is smooth, you can assume xy is smooth, xy is smooth, xy is smooth and the morphism is smooth. For example, in this case xy was smooth but the morphism was not smooth. So any morphism between smooth varieties are not smooth. Careful. Smooth morphism is not just map between smooth variety. No. So here example that the maps, these both are smooth, but the morphism is not smooth. Morphism smooth is the tangential, the surjectivity of at the tangent level. Okay. So xy is smooth. Then assume it is dominant, like fx closure is y. Then this. So now what can the fiber f inverse of y is smooth. And has dimension the expected dimension, which is dimension of x minus dimension of y. And if you take a point x in f inverse of y, then the tangent space at the f inverse of y, if you take, then this is nothing but a kernel of this map df of x. df of x is a map from txx to txy, t of fxy, and you take the kernel, that is nothing but the tangent at the f inverse y. So proof is quite straightforward. So you have this, you take the point, so x to y you have a map, and you have this point y. So at the tangent level, so this is f, so you have this df of x, txx to t of y, y. So y is your fx. So now you have this kernel. Now you see that f inverse of the point y, which is a subset here, this goes to y, right? And what is the tangent space of a point? That is 0. So that means the tangent space of the fiber has to go to kernel, right? So this implies dx of f inverse of y is inside kernel of df at x. Okay, so now this is so without loss of joint, you can assume x, y are affine, because whenever you are doing dimension calculation, these are all affine. You are this over open set, you can do all these things. So without loss of joint, you can assume x and y, everything is affine. But now it is now I don't. This is exercise in commutative algebra or in an affine geometry, that whenever you have a map of x to y, dominant map, affine varieties, and so that means dominant means you have this ky is sitting inside kx, right? You have field extension, and the transidence degree, so you have this dimension of, so this is the transidence degree of ky is dimension of y, and transidence degree of kx over k is the dimension of x. So now if you call this, and then you, the transidence degree is basically the transidence degree of kx, the transidence degree of kx over ky is basically the transidence degree of kx over k minus transidence degree of ky over k. So if you call that, so this is d, then every irreducible component of, this is, suppose this is f of f in, see, f inverse of y has dimension greater than equal to d. So this is one exercise which is a, so I leave it as exercise, maybe I will discuss in one tutorial that this is true. That this is, so this is dimension of the fiber at least is 2. So if you apply this exercise here, then this will say, so this exercise will say that dimension of C is irreducible component of f inverse of y is greater than equal to dimension of x minus dimension of y. Right? Just apply this. Every irreducible component of the fiber has greater than the dimension, this d. D is nothing but transidence, that's what I said, that this dimension of x is transidence degree of kx over k, and this is transidence degree of ky over k. So the transidence degree of kx over ky is nothing but this, right? So now on the other hand, what you know that, so dimension of, so what is dimension of f inverse y? If dimension of f inverse y is basically the maximum of this dimension. Whenever you have some variety which has many components, it can have finitely many components because of Noether's lemma, Noether's theorem. It can have only finitely many components, and you take the maximum of the dimension of those components. That is the dimension of the variety, right? So this dimension of f inverse y is basically the supremum or maximum of this number. Dimension of C, where C is any irreducible component. So this dimension of f inverse y okay, no, sorry. See, now I need to use f is smooth. So since f is smooth, I know that Tx of f inverse of y, x is a point in f inverse y. So that is in the kernel of, so this tangent space of this is in the kernel of dfx, right? So then dimension of this is nothing but it will be less than equal to dimension of kernel of df at x, because after all Tx of f inverse y is a subspace of kernel of dfx, right? Tx of f inverse y is a kernel of dfx. So that will say that, but this is a surjective map. F is smooth. So kernel is a short exact sequence, a vector space. So kernel dimension, this is nothing but dimension of the tangent space of x at x minus dimension of ty of y. Because the map is surjective, kernel dimension is this. But x and y are smooth. So at the tangent space level, so it's same as the dimension of x. So this is equal to same as dimension of x minus dimension of y. So you get 1. The dimension of the tangent space of the fiber is less than equal to dimension of x minus dimension of y. But I want to prove equality, so I want to prove the other inequality, right? So I want to prove the dimension of Tx f inverse y is greater than equal to dimension x minus dimension of y. So how do you do that? So there now you use that this exercise star. I call it star. So from star, dimension of f inverse of y, because it is true for every irreducible component in f inverse y. So this is greater than equal to dimension of x minus dimension of y, which is greater than equal to dimension of Tx of f inverse y. So you use sandwich theorem now, right? So dimension, so now if you use again 1, so dimension of Tx of f inverse of y is greater than equal to dimension of f inverse y greater than equal to dimension. But why is this true? Because tangent space dimension is always greater than the variety dimension. See, this is the tangent space at the tangent space dimension of f inverse y at x. That dimension will be always greater than equal to dimension of f inverse y. But dimension of f inverse y, because of the star, so this inequality, this is from definition, that if you take any point in any variety, the tangent space dimension always is larger than the underlying the dimension. So that is what. But this is because of star. So now you apply 1 and 2. So then results, so apply 1 and 2. So you complete the proof. So the point is that the smooth morphisms are special in the sense that it says that fibers are smooth. So if some map is smooth or not is a question, where it gives you information about every fiber. In general, the fibers may be non-smooth, right? To check if you are interested in the fiber of any morphism and to check that something is smooth, or if you had given some variety, we want to prove that this is smooth. So what you do a family, you construct a map x to y where one fiber is the variety which you are interested. So you construct a family of variety or consider a morphism from x to y, and then you prove that morphism is smooth. So the morphism is smooth will tell you that each point is smooth. So in particular, the variety which you have started with is smooth. So that's how smoothness results are proved in algebraic geometry. See, it's always like you go to something where and you prove that. I was saying in the beginning of this course that it's always morphism. See, this smoothness, this lemma of Chevalier or the lemma of this theorem says that if you prove something map is smooth, gives you some extra information. I mean, fibers are smooth. Right? Directly, if you are given, if something is given, you cannot prove problem. I mean, it's not. But you construct something and then say the map is smooth, so the fiber has to be smooth. So now you see that why it is so important to understand morphisms. So this differential surjectiveness is a very important criteria. Of course, the ambient space x and y has to be smooth. So two things we have used: x and y are smooth, and it is defined. Morphism is smooth. X, y is smooth. Morphism is smooth. When differentially surjective, that will say that each fiber is smooth. That's a very strong statement. Generally, fibers can be very erratic, right? Okay, so I will stop here.